if we want to compare between point B and C, y is the same at B and C, right? So rho GH stays the same. Doesn't change. And if the tube is slightly sloped downward or a little bit upward, that does have an effect on the horizontal range that might be significant. But the rho GY for a couple of millimeters or a millimeter here is going to be pretty small. Okay? Just in the tens or maybe low hundreds of newtons per square meter out of 100,000. Okay, not a big deal. And it'll be in the tens. Okay, so rho GH doesn't change. Significantly, it doesn't change at all in the ideal case, and in the real world, as long as we're kind of careful to get the tube straight, the change is really insignificant, okay? And the difference between water that comes out the higher part of the tube versus the lower, you know, because the tube has a diameter, some of the water's a little higher than others, is very, very insignificant for what we're doing, okay? So we can establish that rho GH doesn't change and that it's not significant. At least you can believe me that it's not significant. So this doesn't change, right? Okay. Well, what is it that you do know the change of?
Velocity.
I'm sorry?
Velocity.
What's the change in velocity? You don't know.
Change in
Okay, so that's not the thing we know.
Change in pressure.
That's the thing we're going to find, huh?
Change in pressure.
What's the change in pressure?
It
goes back to atmosphere.
yeah.
It goes from atmospheric pressure plus rho GY back to just plain
Yeah.
atmospheric pressure.
Okay, well, pressure at B is this, pressure at C is this. If we're going from B to C, what happens to the pressure? Does it increase or decrease?
Decrease.
Why does it decrease?
Because you're taking away the rho GY pressure.
Yeah. Y is positive, that's, this, right? And rho and G are positive, so this is greater than the pressure here, which is atmospheric pressure, right? Now, if we want to be nice and organized about it, it's always a good idea. First we see that. First we intuitively grasp it, and then we check it out. Make sure that we're not being just superstitious. Now, make sure that we're not just doing what we visualize ought to be happening, right?
Mm-hmm.
So in terms of a little more rigor, we say, well, okay, pressure at B equals this, and pressure at C is just atmospheric. So, change in pressure is what?
Rho GY.
Yeah, it's going to be pressure at C minus pressure at B. And we maybe write this down just to be sure we've got the signs right. Make sure the formalism works and confirms or corrects our intuition, right? So that's pressure of the atmosphere minus pressure of the atmosphere plus rho GY, and that equals negative rho GY. Okay, well then, one half rho V squared changes by plus rho GY. Okay? Now that's positive. That means that the velocity has to get bigger since rho isn't changing. Now, if you're in the high temperature wind tunnel, you got density changes, it's not so simple, okay? You gotta be a little more careful, and we're not gonna go too deep into trying to reason that one out. It's beyond the scope of what we really want to do, although we'll, we talk about it a little bit, just to understand that we have this model, and then there's a more complicated model. And if you get into fluid dynamics at some point in your life, you'll get to deal with those. Okay? Okay, so you'll have been forewarned, but here's a big Bernoullis equation still holds. Okay? Okay, well, okay, so 1/2 rho v squared changes by this, right? Okay, what's v here? Well, at b, 1/2 rho v squared is essentially 0. Why is that? It's because if you multiply the cross-sectional area of the tube by this velocity, it's the same as if you multiply the cross-sectional area of the cylinder by this velocity, right? Well, the cylinder is like at least 30 times the diameter of the tube, which means it's 30 squared or close to 1,000 times the cross-sectional area. And if you've done the problems with the cross-sectional areas and velocity and stuff and are getting a grasp on that, you'll believe then that this velocity is in the order of 1,000 times this velocity, at least for the system that we observed, right? And I can then say this is essentially 0 provided a big diameter ratio. In other words, the cylinder is a lot bigger around than the tube, okay? Which is the case for our system. Now, there's a warning there. If the tube gets big enough, then this velocity starts becoming significant, because the bigger the tube, the faster the water is going to go down, right? So 1/2 rho v squared isn't automatically negligible, so we better write down why we say it's negligible here, okay? So the change in 1/2 rho v squared is pretty much, didn't leave myself enough room, but I think I can see just a little bit more in here. I'm going to say that the change in 1/2 rho v squared, since 1/2 rho v squared starts out at pretty much 0, the change is just 1/2 rho times whatever v is at point C. Okay? So thus, one half rho VC squared equals rho GY. Now, what then is VC?